Welcome to the shape of space matrices. In this lesson, I'm going to cover several different topics. Cofactors in the adjugate matrices. These are related to the determinant. Then there's a different topic on the vec operation. And then I'll conclude with talking about the Moore-Penrose inverse and the permutation matrices. I talked about the minor of a matrix a little bit earlier in another lesson. I'm going to go into a bit more detail here. So a minor of a matrix A is a determinant of some smaller square matrix generated from A by removing one or more of its rows and columns. Minors obtained by removing just one row and one column from square matrices are known as first minors. These are the ones we're interested in here. The ij cofactor of A, denoted Cij, is the first minor of A formed by removing row I and column J of A, and that's denoted by Mij, and then multiplying the first minor by minus 1 to the I plus j power. So in other words, C sub ij equals minus 1 I plus j times Mij. We can look at an example here to maybe help clarify. So let's take matrix A given by this, and we'll compute one of the cofactors, C22. That means we need to remove the second column and the second row, and what's left is 1, 3, 3, and 5. Then we take minus 1 to the 2 plus 2 power, so that's just going to be 1. And then the determinant of a 2 by 2 matrix is just the one, it's just the product of the diagonal minus the product of the diagonal going the other direction. So we have that here, so we get a minus 4. Then there's something called the cofactor matrix. If you take all the cofactors, so C11, C12, C13, and so forth, and then put them in a matrix, you get what's called the cofactor matrix. So we computed one of the elements of the cofactor matrix for A. That was the C22 minus 4. And if you did C11, you would get minus 11. I mean, there's some work to do that. I'm not expecting you to just see that immediately, but if you did all the other ones, you would get this full matrix here. And we have some properties. The determinant of a matrix A, whose elements in position ij or A sub ij, can be determined along column J given by this formula here. So you take the elements of A and you multiply it times these different cofactors. Okay, so that's typically a longer way of getting the determinant, but sometimes you need this in a proof, so you'll just make use of the formula in a proof, but not necessarily for computation. And then you could also do the computation along the rows. You notice here we're just shifting the indices here, and this is also a valid formula for the determinant of A. The transpose of the cofactor matrix for a matrix A is called the adjugate matrix and is denoted as AdJ of A, adjugate of A. It can be proved, and I'll give you a reference to this, that the inverse of a matrix A, assuming the inverse exists, is the reciprocal of the determinant times the adjugate matrix. So we have this formula for A inverse. And again, this may be useful in some proofs. There's a lot of information and properties on adjugates. I'm not going to go into them here, but the Wikipedia article, Adjugate Matrix, has a lot more information on that particular type of matrix. We have another concept here. This is not related to the cofactor and adjugate matrices that we talked about in the previous slides. It's called the Vec operation. It's pretty simple. If you have an n by m matrix A, then you just take its columns and you stack one above the other to create a column vector representing the entire matrix A. So I drew it here as a transpose only because it would have gone off of the page. So you take, this is the first column from A and the second all the way down to the nth column of A. And as I say, this would be going in this direction here. So I created it as a transpose. You'll see when I give you an example exactly what I mean. If A is a symmetric matrix, in other words, A equals A transpose, and the vec of A equals the vec of A transpose. And here's an example. Here we have a vector matrix A, 3 by 3, and the vec is just the first column here. Then you take the second column of A and you put that underneath, and then the third column of A and you put that underneath, and you just get one vector that has all the elements of A in the order of first column, second column, third column of A. We have a couple theorems on this slide relating the Vec operation, the trace operation, and the Kronecker product. The first one relates the Vec operation and the trace. So we have two matrices A and B of the same dimension, m by n, and the theorem says that the transpose of vec A times vec B equals a trace of A transpose B. So let's look at this side of it first. We have vec A transpose, that's a row vector times a column vector B. Now they both have the same number of elements, and in fact you're multiplying elements with the same indices together and adding them up, which is this expression here. On the other hand, if you look at trace A transpose B, this equals the sum over J of A transpose B, taking the element JJ, and then this equals the sum over all the elements in A, B multiplied together that have the same indices. In other words, the same thing as we had here. Okay, so you may need to think about this bottom one's a little bit harder to visualize. On the next slide, I'll actually expand this out for a simple example. That may help see things better. Then the second theorem relates vec and the Kronecker product, and it tells us that if we have two column vectors, u and v, the vec of u v transpose equals the Kronecker product of v with u. So we'll just let v equal this vector here. And again, I didn't want to run off the page, so I wrote these as transpose, but keep in mind u and v are column vectors. Then we have that u times v transpose is an m by n matrix. Column I equals v sub I, so the scalar times u. And on the other hand, v Kronecker product with u is an m by n by 1 matrix given by this expression here. And so the ith element in this is actually the same as the column I from this expression here. Okay, and I'll give you, on the next slide, I'll work through an example that may help visualize this a little bit better. I have a couple of examples on this slide to further illustrate the two proofs from the theorems on the previous slide. So the first theorem, we had this expression, and as you recall, this was a row vector times a column vector. They were both of the same size, and effectively we were multiplying elements with the same indices and adding them together, and we got this here. It was the other part of the theorem that was harder to see, and that's what I wanted to expand out here. So if we just take 2 by 2 matrices, A and B, we take A transpose, you notice the indices are, this is really the first row of A, this is the second row of A, and then when you take the transpose, you get this here. Multiply that times B, then you multiply it out. We only need the diagonal elements because we're going to take the trace. So we multiply this row times this column, we get that, and then this row times this column, we get this. Then we take the trace of this, and we get A11, B11, A21 times B21. You notice we get all combinations of elements from A and B with the same indices multiplied together and then added, which is this. Okay, if this doesn't convince you, you may want to try 3 by 3 matrices and just work through the details, and you'll see that the trace of the A transpose B gives you all the possible products of elements from A and B that have the same indices, and then add it together. Okay, so the second theorem, I'll give you an example of that also. So we have U of V transpose. That was one side of the theorem, and we took the vec of that after we computed it. So we have a column vector U, row vector V. It's basically the outer product. And then column I of this is V sub IU. It's this thing here. And when you take the vec of that, it's just stacking the columns one on top of the other. And then the claim is that the vec of this is equal to V kronecker product with U. So we take V kronecker product with U, and it would be V times U1, U2, Vm. Be this thing here. And again, we're going down a column, but I'm writing it as a transpose, otherwise it would go off the page. And then you would take V2 times that, and that would be the next column stacked underneath, which I didn't draw here. And then you have dot, 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 and eventually you get the Vn times all these, and that would be the last m elements in your vector here. So these two are equal when you express them as we've shown here. So hopefully that helps. If you get stuck with some of these proofs, I think the easiest thing is to take an example, either a 2 by 2 or 3 by 3. In this case, I kept it the same dimensions, m and n, but I just wrote it out in a little bit more detail. Okay, so the good news is once you prove these things, you can just use the results and not deal with the internals of the proof itself. So that maybe will make things a little bit easier as we go forward. Theorem 72. For any matrices A, B, and C where the product A, B, C is defined, the following identity holds. The vec of A times B times C equals the kronecker product of C transpose with A times vec of B. Okay, so this looks kind of weird. And the first time I saw it, I said, well, how could this really be useful? It looks like just a result that the author threw into his book to fill space. But it turns out that's far from the truth. This is a very useful result that comes up a lot in matrix calculus where you want to convert from different formats. So with that in mind, let's take a look at the proof. The key to the proof is to represent each column of B as the outer product of two vectors. So let B sub I be column I of B, and E sub I be column I of the identity matrix. In other words, E sub I is the column vector that has a 1 in position I and a 0 everywhere else. Then B sub I times the transpose of E sub I is a matrix whose ith column is B sub I and all of their entries are 0. And then if you just add these up, you're going to get B. Okay, and that's the trick to the theorem. So what we do is, just to give you the plan, we're going to take the vec of A, this term here, times C. So this is not B yet. And then at the end, we're going to do a summation over all of these to get B. But first we'll work with this bit of the problem. So going from here to here, I just grouped the first two terms and the last two. That's the associative law. And then I took this and I wrote it this way here. So the transpose of this is E sub I transpose times the transpose of the transpose of C, which is C. So this equals this. Then we note that these two terms, A, B, I, and C transpose E, I, are column vectors. Of course, the transpose of this is a row vector. The reason I emphasize that is we can use theorem 71 on this here. And that's what I've done down here. I've just copied this up here. Then I'm using theorem 71. So I let U equal ABI, and then V equals CTE sub I. We get this. Give me a second to think about that. Okay, and then going from here to here, we use the mixed product property of the Kronecker product. And that just says this is equal to taking the Kronecker product of this first term was the first term here, and then multiplying that times the Kronecker product of the second term with the second term. That's this. And then we use theorem 71 again on just this second part of the expression. And we get this equals the vec of B sub I, E sub I transpose. So going all the way back to here, this term, which we've worked through, equals this last thing here. So I've just copied the beginning and the end of our computation here. Okay, now we're ready to prove this result. So we start with vec ABC, and then we plug in B. Remember, B equals this. We plug in this for B. Then we can bring out the summation, and then we get vec A, B sub I, E sub I transpose C. And then this equals this, right? That was our result that we proved up front. And then this doesn't involve any of the I in it, so we can pull that out. And then we just get this summation here. We can bring the summation into the vec, this here. And then this is B. And so we get our result. Okay, so a pretty long proof, a bit complicated. And as I say, this is quite useful. The way I remember it is you take this last term here and put it first and make a transpose of it. And then it's Kronecker product was the very first term. And then you have the middle term being vec outside of this. So we'll see this again later in the next set of videos I do on matrix calculus. Changing directions yet again in this lesson, I want to cover another topic that I mentioned before, but I didn't actually get to the definition, which I'll do here. So the Moore-Penrose inverse, sometimes the pseudo-inverse or generalized inverse of a matrix A, denoted by A plus, is the most widely known generalization of the inverse matrix. The pseudo-inverse applies even to matrices that are not square or not invertible. So that's kind of the utility here. It was discovered independently by 3 different people at different times. So apparently it wasn't seen as being useful, given how long it took before it took hold. A common use of the pseudo-inverse is to compute a best fit, least squares approximate solution to a system of linear equations that lacks an exact solution. I'm actually going to have a series of lessons on least squares. It's the very end of this sequence of lessons that I'm preparing, but eventually I'll get to it. Another use is to find the minimum Euclidean norm solution to a system of linear equations with multiple solutions. The pseudo-inverse facilitates the statement and proof of results in linear algebra. We'll see this in some of the lectures I'm going to do on matrix calculus. So here's the definition. You can have either a real or complex matrix A. The Moore-Penrose inverse, A plus, is the unique matrix satisfying the following 4 conditions. So you have this one here, A times the pseudo-inverse of A times A equals A. And then you can just switch it up a little bit here. The pseudo-inverse of A times the pseudo-inverse of A equals the pseudo-inverse of A. And then you have A times the pseudo-inverse, taking the complex conjugate, returns the same matrix. And then you can just shift the order, take the complex conjugate, and you get the same matrix. Okay, so those 4 properties uniquely define a pseudo-inverse. I'm not going to prove that they force you to have a unique solution, but that in fact is the case. There's several properties of the Moore-Penrose inverse, and I'll mention those on the next slide. Okay, so we have a number of properties here. If A is invertible, then the pseudo-inverse equals A inverse, so that's desirable. If A is of full column rank, in other words, the columns are independent, then the pseudo-inverse equals this. So whenever you have linearly independent columns, you get a formula for the pseudo-inverse, which is helpful, and we make use of this later on. If A has full row rank, in other words, the rows are independent, then you get this different formula, but you do get a formula for the pseudo-inverse. The pseudo-inverse of the pseudo-inverse equals A, so you have another characteristic that makes it similar to the regular inverse. The pseudo-inverse commutes with transposition, complex conjugate, and taking the conjugate transpose. In other words, the pseudo-inverse of A transpose equals the transpose of the pseudo-inverse. The pseudo-inverse of the conjugate of A, that's where you take the complex conjugate of every entry in A, that equals the complex conjugate of the pseudo-inverse of A. And then the pseudo-inverse of the complex conjugate of A equals the complex conjugate of the pseudo-inverse of A. The pseudo-inverse of a scalar multiple of A is a reciprocal multiple of the pseudo-inverse. So in other words, this here, assuming alpha does not equal 0. The pseudo-inverse provides the least, and I said this on the last slide, but I'm writing in here in a little bit more detail. The pseudo-inverse provides the least squares solution to AX equals B, minimizing the Euclidean norm of the matrix AX minus B. Okay, we have one more topic in this lesson, again, not related to the previous topics. I'm trying to kind of fit things into lessons roughly the same size, and so I put a few unrelated things together here. Again, I talked about this earlier, but I want to just emphasize it. The concept of a permutation matrix. It's a square binary matrix that has a single one in each row and a single one in each column, with all the other entries being 0. An n by n permutation matrix can represent a permutation of n elements, pre-multiplying an n-row matrix M by a permutation matrix P, forming the matrix PM results from permuting the rows. We saw this before. While post-multiplying an n-column matrix M, forming the matrix MP, permutes the columns of M. Every permutation matrix P is orthogonal, i.e. its inverse is equal to its transpose. Okay, that's a new result. I don't believe I mentioned that before. Then I'm just giving you another example here of permutation matrix. So we have this 3 by 3 permutation matrix times this matrix A. And you notice that we're multiplying on the left, so we're pre-multiplying. And that would do a row permutation. So row 1 of this matrix here becomes row 2. Row 2 becomes row 1. And row 3 stays where it is. We didn't change anything here. Okay, so a bit of a repeat from something I mentioned before, but it doesn't hurt to emphasize some points, which I've done here. Okay, so that's the last slide in this lesson. I have a few more on the topic of matrices, and then we'll get into matrix calculus.